Good morning. Hopefully everyone's doing okay. And today we're going to be looking at the analysis for Lab 13B. So hopefully you got a chance to watch the walkthrough. And remember that we said that this difference from the original freezing point, 44 degrees Celsius, to our new freezing point of 37 degrees Celsius. All right, so if that is our change in freezing point, it works like this. We have our original freezing point we said is 44 degrees Celsius, and we have a new freezing point of 37. All right, so now we're going to use this information to crank out our molality and finally the molar mass of our solute. And remember, I don't care how close you get, I just care that you tried, okay? So don't panic if you got 5 billion% error, it doesn't matter, all right? Okay, here we go. We went from 44 degrees Celsius to 37 degrees Celsius. Ladies and gentlemen, that is a change of 7 degrees Celsius, but let's also remember that that's a negative because we have depressed the freezing point even further, okay? So we're going to plug that right into here. We know the Kf, fulvoric acid, that's our solvent, is negative 3.9 degrees Celsius. So we're going to take our freezing point depression, negative 7. We're going to take our Kf, negative 3.9, and we're going to plug those right into this equation. And this is going to tell us our molality. All right, I got 1.8 molal. That means we have 1.8 moles of solute per kilogram of solvent. Okay, here's the deal. We're going to use this equation to find out how many moles of benzoic acid we have in our solvent. And you know that you used 16 grams of solvent. Ladies and gentlemen, really easy to get that into kilograms. You just divide by 1,000. So this, when we flip this equation around, it says we're going to use the mass of lauric acid in kilograms, not grams, and the molality of the solution to find the moles of benzoic acid used. We know the molality. We just calculated it right up here, 1.8. So that's going to go right here, 1.8 molal times, let's remember that this molality, it's moles per kilogram. See it right here? And now we're going to multiply that by our mass in kilograms, 0.016. For those of you out there that are following along, boop, boop, kilograms cancel. Leaves our answer in moles. So, how many moles of our solute do we have? 1.8 times 0.016 is 0.029 moles of benzoic acid. All right, now we know that we used 2 grams of benzoic acid, and because of our calculations, we know that we had 0.029 moles of benzoic acid in the solution. So look what it says. It says your answer to number 7 goes right here. That means it goes right here. So If number of moles we have equals grams over molar mass, then molar mass is in grams per mole. So that means we got 2 grams divided by 0.029 moles. How many grams per 1 mole is this? 2 divided by 0.029. Boom! 68.9 grams per mole. All right, this is our experimental value, 68.9 grams per mole, is what our data tells us is the molar mass. Now, we're going to compare that to the actual molar mass. Ladies and gentlemen, we've been doing this since chapter 7, calculating molar mass. So here, we've got 6 carbons. They're each 12 grams, plus 5 hydrogens, they're each 1, plus another carbon, 2 oxygens, and another hydrogen. We get a molar mass of 122 grams. This is our accepted value. And we're going to plug these in to get our percent error. I don't care how big it is. Okay, we'll all be freaks together, right? So let's take our numbers. 68.9 grams is our experimental value minus our accepted value. And we're going to divide all that by our accepted value, and we're going to multiply that by 100. So here we go. 68.9 minus 122. Let's take that answer and divide it again by 122 and multiply by 100. I got 43.5% error, which, you know what? Considering how chaotic stuff is, not too bad. And we're going to leave it like that. So hopefully you got something similar. All right, I'll see you later.